Today I will talk about the introduction of birational classification theory of algebraic variety. Sorry, the slide being read again. Okay. Sorry. Okay, today I will talk about the birational classification theory of algebraic varieties. Okay, what is algebraic geometry? At first, we give the definition of algebraic variety. An algebraic variety is a zero locus of polynomial functions. For example, the zero locus of the polynomial x minus y in the real plane is a line, and the zero locus of x squared plus y squared minus z squared in R3 it is a cone, and such that in R3 the zero locus of the set of two polynomials is a parabola. And if today we work on the projective space, then the zero locus of x squared plus y squared, sorry, here should be minus z squared, not equal, sorry. The zero locus of x squared plus y squared minus z squared will be a circle. And the curve y equal to sine x is not an algebraic variety because the defining equation is not a polynomial. Such as this one. The red guy, the parabola, is defined by x squared minus y equal to 0, so it is an algebraic variety. The cuspidal curve divided by x cubed minus y squared is 0, so it is also an algebraic variety. But the sine curve is not an algebraic variety because the defining equation sine x minus y equal to 0. This is not an polynomial. Okay. Algebraic geometry is the mathematical branch that studies the geometric properties of algebraic varieties. And we call two algebraic varieties are isomorphic. That is, they have same structure as algebraic variety. For example, the parabola and the x-axis is isomorphic because we can project we have a one-to-one and onto projection from the parabola to x-axis. And for isomorphic varieties, we have this notation. Okay. Okay. Then, for example, the parabola and the line is isomorphic because we have a one-to-one and onto projection from the parabola to the line. And cuspidal curve and the line are not isomorphic. Although this map is bijective one-to-one and onto a map between sets, but the cuspidal curve have a singular point. However, a line is smooth, so they are not isomorphic. And the line and the nodal curve is also non-isomorphic because this map is not bijective. So there are 2 points mapped to the node. So it is another non-isomorphic example. Okay, a question is how to classify algebraic varieties. The most natural ways we classify variety is up to isomorphism. However, there are 2 more isomorphism classes of algebraic varieties. So if we want to classify up to isomorphism, it is 2 more things to classify it. On the other hand, if we regard varieties with almost isomorphic global structure into the same class, then it will be a more feasible question. Okay, so for the almost isomorphic classification, here is the work of birational geometry. Two algebraic varieties are called birational equivalent if they have open dense subsets that are isomorphic. That is, they do not need completely isomorphic to each other. But after we removing a small closed subset, the remaining parts are isomorphic, then they are birational. And the notation is that. Now we given some example birational of birational equivalence. For example, the complex plane and the sphere are birational equivalent if we regard the sphere as a one-dimensional projective space over a complex number field. And a cone is birational equivalent to a cylinder. And two smooth compact Riemann surfaces, that is one-dimensional projective curve, one-dimensional complex projective curve, which different genus are not birationally equivalent to each other. For example, that is why a sphere are birational equivalent to a plane. They are actually non-isomorphic because sphere is compact, but plane is non-compact. However, after we removing the north pole, we have a one-to-one and onto projection from the sphere removing a point to the plane. So we see that plane and the sphere non-isomorphic, but after we sphere removing one point, then the remaining parts are isomorphic to a plane. So that is an example of birational equivalence. Okay, if today we have bad singularity, there may be something globally looks like very straight, but they are still isomorphic. For example, a cylinder and a cone looks like very different, right? Because there is a bad singularity. Here is smooth, but as the colored lines, at least colored line have a one-one onto mapping. Because after we removing the cone, the vertex of the cone, then the remaining part is isomorphic to a cylinder remove a circle. Yes. Here we need remove this circle, and here we remove the singular point. Then the remaining parts are isomorphic to each other. So in some sense, if there are for a singular variety, it is possible that two birational equivalency looks like very different to each other, very different to each other. However, after we removing the singular locus, the smooth parts are almost isomorphic. This is another example for birational equivalence. The plane is birational equivalent to the surface at here, defined by this equation. Here is the singularity. However, after we remove this point on the plane, the remaining guys are isomorphic to this surface remove this singular point. And for example, today for Riemann surface with different genus, they are not birational equivalent to each other. Because we cannot by removing finite many points on a torus to let the remaining part isomorphic to the open subset of a sphere. So they are not birational equivalent. And in birational equivalence, there are two important theorems. The first one is the theorem proved by Chinese mathematician Wei Liang Zhou. He proved that every algebraic variety over a complex number always birational equivalent to a projective, hence complex variety. That is an compactification. For example, the compactification of the plane is the sphere. Because we can regard the sphere is we adding the infinity point to the plane and then the plane including the plane with one more point as infinity becoming the sphere. This point is the infinity point. So sphere is compactification of a plane. Another important theorem is proved by Professor Hironaka. He gets Fields Medal by this theorem. That is, for any complex projective variety, we always have a resolution of singularity. That is, there is a smooth projective variety x prime birational equivalent to x, and there is a surjective morphism to x. For example, the resolution of the cone is the cylinder, because there is a morphism from cylinder to cone, and beside the singular point, remaining parts are one-to-one and onto. This is an example of Hilonaka's resolution of singularities. So combining the result theorem of Zhou and Hilonaka, we can see every variety over a complex number always birational equivalent to a smooth projective compact variety. Okay. Okay, in the following, every variety are assumed to be over the complex number field. Okay, now assume a projective variety with mild singularity. Mild means that it may be not smooth, but the singularity should be not so bad in some sense. In this case, the top differential form the top differential form on the variety will given an line bundle denoted OKX. It's called the canonical bundle. And two different differential forms will induce isomorphic bundle. So after isomorphism, canonical bundle is well defined as unique. And we let the OK minus KX be the dual bundle of the canonical bundle. In general, given any line bundle, we have an invariant called iTHEMS dimension, which measures the size of global section of the line bundle. This number should be either minus infinity or a non-negative integer less than or equal to the dimension of X. And the Kodaira dimension of a variety is the iTHEMS dimension of its canonical bundle. This is the definition. And one important term is birational equivalent varieties have same Kodaira dimension. This Kodaira actually is the first Japanese field method is canonical Kodaira. Okay. And we regard there are three basic types of projective varieties. That is, one is called general type if the Kodaira dimension equivalent to the dimension. One is called Calabi-Yau type if the Kodaira dimension is 0. And one is called funnel type if the iTHEMS dimension of anti-canonical bundle equivalent to the dimension of X. For example, for smooth projective curve, if it has no genus, then it is isomorphic to one-dimensional projective space. It is funnel type. Genus 3 minutes. Okay. So for example, curve and the hypersurface are always in these basic types. Okay. And the idea, the philosophy of Professor Itaka's schedule is the basic type varieties are the basic element of varieties. Every variety in some sense are compound of these elements. Okay. For example, a smooth projective surface, if either it is already basic type or it is birational to basic type, or it will be in a vibration of curves. So it can regard as a vibration of curve over another curve, and the curve is basic type. An important result is the Enriquez Kodaira classification. That is for smooth projective surface, we always have a good minimal model. And the good minimal model must be one of these forms. Either the minimal model is general type or Calabi-Yau type, or must either be general type, Calabi-Yau type, funnel type. That is already basic type, or it should be a vibration over another curve. And fiber and base are both basic type. And in birational geometry, our goal is such as for a projective variety with mild singularity, if the Kodaira dimension is non-negative, then it will have a minimal model Y such that there is a morphism from Y to another lower dimensional variety, such that all fibers are Calabi-Yau type. And if the Kodaira dimension is minus infinity, then we still up to birational equivalent. We will have a morphism to another lower dimensional variety. And in this case, general fibers should be Fano type. That is, if a variety is not in the basic type, we always can replace with a birational model, and that there is a morphism to another lower dimensional variety such that the fibers are basic type. In the first case, we call this guy is a good minimal model. In the second case, this vibration is called a multi-fiber space. Okay, finally, this conjecture is in fact the combination of two important conjectures. The one is called minimal model conjecture. Another is called the abundance conjecture. These two conjectures in lower dimension case, dimension less than 2, it is just a direct result followed from the Enriquez Kodaira classification. In dimension 3, the minimal model conjecture is proved by Professor Shigeru, and the abundance conjecture is proved by Professor Yujiro Kawamata. So 3-dimension case, this conjecture is okay. However, if the dimension is at least 4, these two conjecture is still an open problem until now. Okay. Yeah, that is our goal, or that is a goal of birational geometry. Okay. Okay, thank you for listening.
So questions from young non-mathematician. First, any question? Okay, so question from mathematician or senior people. Yes.
I think it's a very basic question. You told us that the sphere is not birational equivalent.
A sphere at
the torus.
Yes.
But suppose you remove a point from the sphere, then it gives an open disk.
Yes.
And then from the torus, you can remove the meridian and the longitude to cut open to get the open square. So at least this open disk and this open square is open.
Yes, but in this case, they are not birational equivalent. It's because we regard the removed subset should be a closed subset in Zariski topology. That is, this closed subset should be an algebraic subvariety of this variety, of the original variety. If we regard torus as a one-dimensional complex variety, then a circle is not complex, guys. So it is not a algebraic subvariety.
Oh, I see. So we are living in a different type of result. So I don't think
if we regard they are two-dimensional real variety, maybe it is two.
Oh, I see.
Yes.
I have a very basic question. So we had at the start this correspondence between polynomials and these geometric shapes. And now you've allowed to have equivalences with that are basically almost similar, but you remove finite numbers, finite points. Can you then exit polynomial space? Because is it possible to? It seems to me it's possible to add finite points and then it's no longer a polynomial anymore. Is that
maybe?
And in other words, is there like a theory maybe for almost polynomials? Maybe.
In this case, if we remove finite many points of an algebraic variety, it is not an traditional case. This is not a traditional definition of algebraic variety, but we have a generalization of algebraic this called scheme. This called algebraic scheme. That is, in this case, what you say, removing finite point from an algebraic variety, it will becoming it will not a variety, but it will becoming a scheme. So the scheme, to explain what is a scheme, maybe here need to introduce some abstract algebra. But what you say is this guy exists in another algebraic geometry theory, but it is not a variety.
But so so polynomials. Is there like a one-to-one correspondence between polynomials and these birational classes?
No, two different. Could have different polynomial to give the same algebraic isomorphic variety.
But it always has to be a polynomial. It can't be something else. Maybe I'm
For example, the parabola and the line are isomorphic, but they come from different polynomial.
Any other questions? Ah, yes, please.
So how rigid is the birational structure?
How rich?
Rigid.
Rigid.
So I mean, can you infinitesimally deform a birational structure?
Maybe under after a deformation, it could cause it could construct another thing being non-birational. That is, in a deformation space, the different fiber could be non-birational to each other. And here is even to deforming a smooth guide into a singular guide. For example,
Okay.
one can deform a torus being two lines. A torus can be deformed to two one-dimensional complex projective space.
Any other? Yes.
Yeah, me. So if you already explained, I'm sorry. So would you describe how your study is related to what you taught?
What I taught?
Yeah.
Okay. In fact, my personal study is study on algebraic fiber space. That is, for example, my PhD thesis is study between a morphism. For example, there is a morphism from X to Y and F, and F is a fiber. My study is on what is the relation between the codial dimension of X and F and Y, because the codial dimension is the basic one of the basic element in classification of algebraic geometry, and my work is focused on, for a morphism, what's the relation of these guys. And here is a very important conjecture in algebraic geometry called Chi-Kang conjecture. That is, our conjecture is the codial dimension of X will greater than or equal to the codial dimension of F plus the codial dimension of Y. And this guys is remaining open for higher dimensional, but lower dimensional has been improved. Yes, this is my personal style. Thank you.
Yes.
You kindly gave relatively simple example in building the curves and so on. But there are maybe easy problems. But my question is, are there number one problem in algebraic geometry which has not been solved for a long time, but very interesting? For example, you're working or some other work.
In fact, the minimal model conjecture is not only this. This is not the minimal model conjecture itself. It is just, if we assuming minimal model conjecture is true, then what corollary we will get. In fact, the minimal model conjecture is that in this graphic, we start from a variety. If X is not minimal, then there is a birational morphism. There is a surjective birational morphism to another algebraic variety. So that is why we call the goal of these guys called minimal. This is because if a variety is not in this form, then it must have a morphism to a birational but smaller variety. And one of the number one question of algebraic geometry is such. We know we always have contraction, but how do we ensure after finite many contractions it will becoming a minimal and it will not be in infinity contract and the contraction sequence will not be in infinity continuous. This is one of the number one question of birational geometry.
Iso-san, yes.
Well, yeah, I would like to understand more about this codilient dimension.
Yes.
So where isomorphism where is mapping from one space to that,
Yes.
and where if I understand correctly, so where you discussed the behavior of singularities of some algebraic variety. And yeah, so my question is so if, for example, if we define field theory or topological field theory on these spaces, what's the difference between the behavior of field theory with different codiral dimensions? Is it possible to explain codiral dimension from that perspective?
I am not sure. One way to explain the codiral dimension is that, in fact, we have for the canonical bundle, we can let it be in. We can give a self-tensor product, and in fact, what I said measure the global section of the line bundle is that if in general the dimension of global section of the self-intercept of the self-tensor of the canonical bundle well proportional to some power of n, and the growth is how many dimensional of polynomial. We say this number is a codiral dimension. So it may be another way to realize codiral dimension is on how many global sections this sheet has how many global sections after self-tensor. But if we want to have a field theory realization,
Well, yeah, so it's not so usually we use, for example, homology or homotopy to classify manifold.
Yes.
And is that related to this topological quantity?
maybe not, because it is possible. Maybe not so direct, because in my realization, it is possible to have homeomorphic varieties that have different codal dimensions, if my memory is true. Because when we defining an algebraic variety, it is not only topological structure, it is also have algebraic structure. For example, any different K3 surface are always diffeomorphic to each other, in particular homeomorphic. But two different K3 surfaces have completely different algebraic structure. So I think it cannot only realize it by topological invariant, because same topological space can be in different algebraic variety if the algebraic structure is different.
I have a question about the mild singularity.
Yeah.
And what is the difference between mild singularity and normal singularity? So I am interested in the singularity because in general relativity, a black hole has singularity.
Yes.
And when we encounter the singularity, so we'll give up to understand the singularity anymore, furthermore. But is there any possibility that you can do some more analysis to understand the property of singularity?
Okay, in fact, for our real definition of mild singularity is this. Now, at first, from the theorem of Hironaka, if X is singular, and by Hironaka's theorem, here is the smooth sky birational equivalent to it. Only resolving singularity and smooth part are equivalent. Then, in this case, we can regard the canonical bundle. We have a relation that the canonical bundle of X prime is the pole-back of canonical bundle of X plus the exceptional divisors. Exceptional divisor means that there are codimension one subset sent to the singularities. Then, in fact, such map is a sequence of a special birational map called blow up. Usually, usually if x is already smooth, then in this blow up, each AI is greater than or equal to 1 if x is smooth. And then we define how bad a singularity is seeing this number. If it is satisfies each AI it can less than 1 but always positive. This guy is called terminal singularity. And this guy, if at least -1, then this guy is called KLT singularity. Full name is Kawamata log terminal singularity. And what we say, usually we say a singularity is mild. Usually means it is terminal or KLT. That is when we resolving the singularities, they will cause too many poles on the preimage of the singular locus. That is usually we strictly define what is mild and what is bad singularity. And for example, this singularity is not KLT. And this singularity is KLT but not terminal. Yeah.
Okay. Yeah, thank you very much. So any further questions? So question from, yes.
So can you give an easy example of, so that one is a bad singularity and the other one is KLT but not terminal.
Yes.
Can you give an example of a terminal singularity?
Terminal singularity. Maybe here is a little difficult to give a very easy example because terminal singularity always have codimension at least 3. So on curve and surface, there is no non-smooth terminal singularity. And the terminal singularity is always appear in at least 3-dimensional or more. Maybe one easy example of terminal singularity is the weighted projective space. That is a finite quotient of a group action to projective space. Maybe this is one easy example.
Thank you very much. So questions from the Zoom audience? If you have, could you unmute yourself and speak up? So if not, let's thank the speaker again. Very interesting. Thank you very much.
这种可以应该很难去处理。
You're talking about that. So you're talking about something.